And this is one of my first times giving a talk remotely, so please feel free to interrupt. Tell me if my audio sucks. Give me, more feedback, the better. I'm going to stop for questions on a regular basis, but also feel free to interrupt. I mean, this is going to be very informal. I'm really excited to give this talk to this audience in particular because I think this work is a nice blend of theory, algorithms, and learning. And I do think we have something, I think, pretty new under the sun here. So also, you'll notice the title is Latent SDEs, not Neural SDEs. I'm trying to be classier than the last time, the last hype cycle. So, okay. So, so just to give you a quick overview of where we're going to go is we're going to generalize the adjoint sensitivity method, developed 50 or 60 years ago for ODEs to SDEs. And I was very surprised that this algorithm did not already exist when we started looking into it. And there actually required two sort of technical contributions to make it basically proved to be sensible and scalable. And then we're going to provide this algorithm that works with arbitrary, fancy, adaptive SDE solvers. We're not just going to do EM for everything. Like we're going to talk about exact SDEs here. We were some of the results we were only able to prove for EM, but we're pretty sure that this all generalizes. All right, and so at the end, we're going to be able to fit large SDE models, like with hundreds of states, or like 100-dimensional states, millions of parameters, no problem, no solving PDEs, just using simple Monte Carlo and automatic differentiation, like vector Jacobian products. Okay, so the motivation for all of this work, other than just what's the next type of neural differential equation can we make, the practical application is in irregularly sampled time series datasets. And this is actually an area where I think machine learning is severely underserving the health community and business community. Like every time I talk to one of Vector's sponsors, they say, okay, I have a whole bunch of data of this customer bought this thing on this day, and then they asked about this product on that day. Or same with patients, right? We have these long medical records, which is different tests done at different times. Here is actual data from a particular patient in an ICU over 48 hours and all the different types of measurements that were being made on them as a function of time. And these are not coming every hour, right? These are just higgledy-piggledy. But most of well, I'd say, there's definitely continuous time models that have existed forever, like continuous time Kalman filters and Gaussian processes. But there's not really a nice way to have a large model with complex dynamics that we can learn scalably and can handle irregularly sampled time series natively. So the sort of goal of why we're looking into SDs in the first place is to be able to handle this type of data. Okay, and so this is actually, now that I look at the audience here, maybe overkill. I'll just say that we're establishing notation, which is that our state of our system is going to be some vector Z. It can be 100-dimensional. F is going to represent our, the function that specifies the time derivative of our state. And that could be specified by a neural network. Who knows? It's just, a function that we're going to parameterize. Of course, when we solve initial value problems, we could use Euler's method, but we would prefer to use adaptive higher order solvers. And also, there's a whole bunch of benefits to using adaptive solvers, which is that they might be able to enforce invariance that you get in a continuous time setting that you would lose if you have a fixed discretization of time. So we did a little bit of work with this, dealing with the setting when we implemented the adjoint sensitivities method in PyTorch and all these automatic differentiation frameworks, which let us build things like the ODE RNN, which is a very simple idea, which says that, okay, a standard RNN has a hidden state that gets updated whenever we have an observation. And there's some little RNN that says, okay, given the new data, how do I update my hidden state? So that's fine, but it doesn't take into account the fact that the time delays are important, and it doesn't have a well-defined state in between observations. So the very basic first thing you might try is to say, well, one of them is just append time to this update, which is also a fine thing to do, but it's doesn't necessarily describe a coherent model. The other one is just to say, oh, no, let's have the hidden state of our system evolve according to an ODE. And then when we implement this, we just, say H prime is some ODE solve of the time delta. And this is nice, right? Because it's, now we can specify how your beliefs should be updating as time goes on. And like, if you're waiting for a friend, even before they get there, there's no new data, but your belief about what's going on with them is updating continuously. However, I want to also advocate for the use of proper latent variable models in the sort of probabilistic sense, where we'll say that, this is kind of a subtle distinction, and I don't want to spend too much time on the talk on it, but RNNs are kind of funny because their hidden state is sort of a belief state that happens to be stored in this vector form. And that's a distinct model class from if we, like a Kalman filter or a hidden Markov model, where we say that there is a hidden state which we don't observe, and then we observe noisy observations, and we have to do inference to learn about the hidden state of the system. And we could use a recurrent null network for that, but the inference is separate from the generation. And I think that this is a really good thing for at least scientific models, where we think that there is a true state of like the population genetics or the customer or the patient that is distinct from our belief about that patient. Okay. And so, one of my favorite model classes is the deep Markov model or deep Kalman filter that was developed by Rahul Krishnan and David Sontag when they were at NYU, which just says, okay, it's like a Kalman filter, but with nonlinear dynamics and nonlinear non-Gaussian observations. This introduces a hard inference problem, but we have a lot of options for integrating outside. Okay, so still warming up with like simple things that don't quite get what we want. The next most sophisticated thing we could do would be to have an ODE latent variable model, where we say that the system that we're trying to model has some hidden state that then evolves deterministically according to some ODE whose dynamics we can learn. And this is kind of, well, it's getting two of the things we wanted. One is continuous time and being able to deal with irregular samples observations. And we've also like separated out the hidden state of the system from our beliefs about it. So we had this paper on like latent ODEs for time series that dealt with this model. Here's a very like toy example of us fitting this model class, where so here in green, the green dots are just data from some toy problem. It's kind of vaguely sinusoidal with noise. These are showing posteriors over the latent trajectories of our state, which doesn't have to be the same dimension as our observed data. And here, this is trying to show F, the dynamics that we're learning. And so we can visualize that as like one of these arrow charts. And this is only a two-dimensional slice of our four-dimensional dynamics. And if we run this and use a variational autoencoder or like integrate out Z to estimate the marginal likelihood of this model, we can fit the likelihood and the dynamics both together at once. Kind of like just doing forward backwards in a hidden Markov model or a Kalman filter, except now everything's nice and nonlinear. Okay, so that's sort of the setup of like what we could do with continuous time, let's say like neural network models before the work that I'm going to talk about. Any questions at this point? Okay, great. Also, before we get into all this, I want to say that I'm still a neophyte to the numerics world, and I'm definitely going to like gloss over some stuff that maybe shouldn't be glossed over or miss some related work. So one of the reasons I am happy to or excited to talk to this audience is I think you guys will probably be able to point me to some stuff that is related to what I'm talking about that I didn't mention, and I will absolutely be grateful for any pointers. Okay, so yeah, so we did actually get this model running, and it's does the best. We have bold numbers when we apply it to this data set of people in intensive care units, and of course we would have we're sort of generalizing previous model classes, so we can't not win in a sense. One thing though that I want to talk about briefly that you can do in continuous time. That didn't help in this instance because I think the data was sampled too densely, is this Poisson thing, which maybe only slightly helped, which is that one of the nice benefits of continuous time is that we can actually condition on the time at which observations were made as a source of information about our latent variable. So in lots of settings, just the fact that an observation was made tells you a lot about the state of the system. Like if I show you two medical histories, and one of them is like, this guy shows up only to his yearly checkups. And another one is this, this person used to show up yearly and now they're showing up all the time getting all sorts of tests done without even knowing the results of those tests. Probably the second guy is like sicker or has something going on with him. And a lot of the models that we use to model time series don't actually let us condition on that information. At least, there's a few like Hawk's process and things like that, but they usually are restricted to having like exponential dynamics or like very simple likelihoods. The cool thing is that if we have to solve an ODE just to evaluate our model, we might as well append something to the state, which is the Poisson rate, this lambda function that just says what is the instantaneous probability of seeing an observation at this time. And that will let us compute Poisson process likelihoods. And we can make this rate function be an arbitrary learned function of the state of our system. So, we can learn things like when you're sick, you're more likely to get this type of test done and all sorts of interesting details. And we can even imagine this setting where there's like more than one type of test being done, kind of like the data on the previous page, where different types of diseases will cause you to have different types of tests, or customers will want to buy different products or whatever. And this is just a proof of concept where the green line is the inferred rate for a particular patient on a particular type of measurement, and the blue bars are the actual observation times for that patient on that time series. So we were able to actually do a pretty good job of automatically, with all of our neural goo everywhere and our approximate inference, still do a decent job of modeling the arrival times jointly with the actual observations.
David, just so I can place this work in my head, this is all work prior to neural ODE stuff?
No, this was stuff, I mean, obviously people have been using Poisson process like this forever, right?
Sure.
This is just something that we did actually we had this in the neural ODES paper as well, just like a very simple demo. And then this is like a follow-up where we actually applied it to real data, and it kind of worked. So
I see it. I guess I'm not familiar with the lingo like ODRNN, right? Is that? Oh,
that was after the neural ODE paper.
Okay.
Yeah, and there was some previous work started saying let's have exponential decays in between, like an RNN in between. And so now we're just saying, hey, if we're going to pay the cost of having this ODE solver in our model, we might as well just go nuts and use whatever dynamics. So anyway, none of this is like all the conceptually novel. It's just that it's just now easy to stick an ODE solve in your model now. So we should go nuts. Okay, so this is all just teasing to set up again the reason. Oh yeah, and code for all this stuff is available. But why don't we want to have ODE models for most of these settings? And the main problem is this deterministic dynamics are just really weird. And in this model, there's uncertainty about the initial state of the system, right? Which we're free to choose time zero. So we could say that's when you first start seeing the patient, or when they're born, or whatever. But there's no space for uncertainty or unobserved interactions or anything in our model that could affect their state, except at the beginning. So if we want to model some complicated trajectory of someone's life, we kind of have to stick enough information into their initial state that we could predict that they're like going to get hit by a car when they're 20 or something. And this seems like a bad way to model. And also, so the state size kind of has to grow with the amount of information in the sequence. And we have this like funny special T0, which we don't think there's anything special about that in terms of the dynamics. Yeah, so there's like been a few works sort of saying, oh, let's have some sort of jump process thing going on here. And I think that's a totally valid way forward as well. But for a number of reasons, we wanted to first look at the infinitesimal noise version of these things. So yeah, so the thing that's missing from those models is the stochastic transition dynamics. And Kelm filters, hidden Markov models, all these guys say that there's every update has some noise that's added. And this is important for just modeling all the little unobserved interactions that happen that we didn't get to see. And so actually there was some work from Maxime Roginski just sort of crossing the T's and dotting the I's, saying, yeah, what happens if I take the infinitesimal limit of one of these deep Markov models or Kalman filters or something? Well, we do actually recover stochastic differential equations. And I mean the classic form that people have been studying for 50 or 60 years. I feel like I need to say that because there's been a whole bunch of papers, like 4 or 5 follow-ups to neural ODEs that say that they're neural SDEs, but they just like add noise to the solver or some sad, like not principled thing that, when you take the infinitesimal limit, you get an ODE again, and it's just like fiddling with the model in some way. Anyway, so I think this audience probably doesn't need an intro to SDEs. I'll just say that we have this ODE part that we were learning before, and then now plus we have this diffusion function, we'll call it sigma, that can also depend on the state. It can also depend on time if we want, and it says how much to depend on some infinitesimal noise. And of course, this is kind of like probabilistic programming in a lot of ways, where we're defining a distribution over functions, but only by defining a sampler. And most of the, if I tell you an F and a sigma, it's probably going to be really hard to actually write down the density over functions like we can for Gaussian processes, for instance. So I just wanted to mention that just to pique Dan's interest. So we're not going to have closed form densities from here on out, which might seem intimidating, and it did to me, but actually things are going to surprisingly work out. So we can do approximate inference very nicely. And I mean, maybe this is, again, overkill for this audience, but basically any setting where we have a lot of tiny interactions, that there's enough of them that the central limit theorem kicks in, then this Brownian norms formulation is already sort of very general. And I think a lot of people see this and they're like, oh, it's just some special case that's chosen with Gaussian noise just for no reason. And it's actually like very general, and it's closed under a lot of transformations that like GPs aren't closed under, for instance. So the basic idea of what we want to do now is we say, okay, this would be a great model class if we could somehow fit SDEs to data. Just like for neural ODEs, like it doesn't take a big brain to say, let's stick parameters in our functions and learn those from data. So that's what we want to do. Any questions about this setup so far? Great.
So I have a question. So the noise is actually really stochastic noise, or it's what we call quench noise. I mean, so it's frozen in the weights of the network. I mean, you're using actually stochastic networks.
I'll say that these functions f and sigma are going to be deterministic functions of their inputs, and then the only stochasticity in this model is going to come from this Brownian motion,
which is a real Brownian motion.
Okay. Yes. I'm not sure in which sense it could not be real, but
real as in the data outside in the world, not randomness in the training or something.
I mean, at this point, we're just defining random variables. So to me, I just think of random variables as representing uncertainty, but like, I guess I'll say I don't think that distinction matters yet at this point.
All right.
Yeah. Okay. So to set up the technical problem of like why it's hard to actually fit these, there's like sort of like 3 technical problems that we're gonna have to fix. So one is just how to compute gradients. So the idea is that we're going to define our f. Well, for ODEs, we just define an f, and then we might want to optimize some scalar loss that depends on the output of integrating this vector valued system. And you could just backprop through the operations of the solver, but it's a little bit weird if your solver is adaptive and it has control flow. And we're going to end up, I would say, the main problem is that we'll end up maybe overflowing and spending too much memory if we have to memorize all these intermediate steps in order to do reverse mode autodiff, which is the only scalable form of.
Sorry, David, could you actually walk us through, what maps to what? So in this ODE formulation, what is the input to the neural net? And
Yeah. So the idea is that the neural network is this F. So its input would be Z and T. and it's the parameters of the neural network would be theta. Yeah,
and this is an RNN we should think of, or just a very deep net?
Well, that's a great question. So yeah, I would say this F is not necessarily a deep net at all. It could just be like one layer. And then when we stick a whole bunch of these, like when we solve this ODE, it's kind of like a very deep residual network where if you think of like an Euler solver, it's going to evaluate F, update Z in that direction, evaluate F again at that new point, evaluate Z in that direction. So this F is a tiny network usually, but by sticking it inside of an ODE, we've kind of defined this like infinitely deep residual network, if you want to think about it that way.
And is it like an infinitely deep network where the parameters are shared over the layers?
Yeah. So we could make theta depend on t, but without loss of generality, we can also have a fixed theta and let t be an input to the neural network. Like neither is more general than the other. It's just a question of sort of how do you parameterize these things. So I want to say though that I think maybe all my discussion of neural networks has been slightly confusing because all of the stuff that I'm going to talk about in this whole lecture is true no matter whether F is a neural network or not. It's just a parametric function, and its parameters are theta. Okay, so there's a few ways to. Okay, so there's a very old method from Pontryagin who kind of outlined it, and the early neural network people like Jan LeCun in the 70s were talking about this method of, well, I would call it like continuous time backpropagation, where we basically say that if I wanted to get the gradient of my scalar loss with respect to my parameters, in a standard residual network, I end up just having to compute a whole bunch of like vector valued gradients times Jacobians, and I do this, backwards in time, or backwards, starting from the end of the network backwards to the beginning. Each of these operations is pretty cheap. It costs about the same as just the corresponding forward operation that we're computing the Jacobian of. We never have to instantiate the Jacobians. We just compute Jacobian vector products implicitly, and that's always cheap. And so, in the ODE setting, we can take the infinitesimal limit of these updates and end up with another ODE that says how to compute the scalar value loss with respect to the parameters. And what that has to do is just solve an ODE backwards in time whose dynamics are given by a vector times a Jacobian. So I would love to spend like a lot of time on this algorithm, but the key takeaway is that there just happens to be a continuous time of backprop, and the operations that define its dynamics are already things that we compute with automatic differentiation for any parametric function already. So it's easy to write a little bit of pseudocode. If F is my parametric function on the forward pass, I can define this augmented set of dynamics that has F, and then this is like the adjoint dynamics, this A, which is the loss of the scalar output with respect to the state at any one time. And then this dynamics is the same thing I'm drawing over here. It's just a vector Jovian product that says how does that loss relate to the parameters that are already there, which are fixed. So the punchline is that I can get all my gradients with another call to an ODE solver that runs backwards in time. Right, and this is like I'm trying to make it clear with this citation that everyone this is not secret. This is not new. The only thing that we did in the neural ODES paper algorithmically really was to just take these formulas and then put them into automatic differentiation without ever instantiating Jacobians, which no one had ever used all these tricks in one. Everyone had used some of these tricks in different places, but no one had ever put them all in one spot before. Okay, any questions about this continuous time background? Okay, so the cool thing about this is that this reduces the memory cost of doing backprop to just the cost of computing one layer's activations. So normally when we want to do the reverse mode chain rule, we have to store all the intermediate quantities of the functions we've composed. The cool thing about ODEs is that in principle, like up to numerical error, you can just run the system forwards, get to the end, and then start there and run the system backwards with just negative dynamics and reconstruct your trajectory to arbitrary accuracy. And this is where the numerics people always get mad at me and they say, no, you can't do that. What if the system is like not stiff in the forward pass and stiff in the reverse pass? And I'll say, yes. If it is, then we can't necessarily save memory in this way, or if we do, we have to like recompute things from the forward direction. But I guess I'll also say, it's the ODE solver's job to control error. If you believe it control error except in the forward direction, usually it's okay to ask it to control error in the reverse direction. But that could be a real issue, and once in a while it does hurt us. But the point is that, to construct the dynamics of our backward system, if we wanted to like call an ODE solver to run the backwards dynamics like forward in time, you just have to stick a negative sign in front of the dynamics and a negative sign in front of t. Okay, so that's just like a nice fun trick that you can use if you have a reversible system. And people had also been building neural networks before this that were like reversible networks, just for exactly the same reason, to save memory during training. Okay, so just to make it clear, that pseudocode, I'm just going to write it here because we're going to come back to this when we generalize it to SDEs. The idea is that I had some function f that I solved forward in time, and computed the scalar loss as a function of the output of the system, set of t1. And then to compute all the gradients that I need to train the system, I just construct this augmented dynamics that I showed you before. It's just like the, f and then this vector Jacobian product and this other one. And I get all of the answers by just starting my augmented state at the final time point and then running a big ODE integration backwards in time. Okay. So, as an academic, my first thought is, oh, why don't I just use the exact same trick that I used to get the last paper out in a slightly more general setting and get an even bigger result, right? And so the whole idea of going to this paper was, yeah, okay, we'll just apply the SDEs, like how hard can it be? And actually, a little bit of the math had been worked out for what the dynamics of the adjoint sensitivity would be in the reverse direction. But there was a whole bunch of mathematical difficulties and algorithmic difficulties. And it's kind of nice because some pretty, I'd say, sophisticated people, like, again, Senator Majinski and some other people, wrote papers titled Neural SDEs, but they used forward mode autodiff to get gradients, which doesn't scale. You have to do a separate forward pass for every single parameter in your system if you're using forward mode. And there's also a bunch of mathematical problems with trying to run SDEs backwards. And so I'm not going to go into like...
Actually, it's essential for you for the network to be fully reversible. Otherwise, it doesn't work.
No. So that's a great point. Yeah, you're basically asking, does our f here need to be an invertible function?
Right.
And no, it doesn't.
So I thought you were saying it backwards, so you need to somehow reverse the dynamics.
Well, that's the beauty. So yes, for the earlier work that was constructing reversible neural networks, they had to make every layer invertible, and that was a big restriction. The beautiful part about the ODE setting is that to invert the ODE, I only need to negate the instantaneous dynamics. So this function doesn't have to be invertible or have any nice properties except for it just to be, absolutely differentiable. And Lipschitz, like the usual things that we require to make sure that the solution to the ODE is unique.
So in particular, it can be distributive dynamics in some sense. I mean,
yes, exactly.
Okay. Good.
Yeah, this can handle anything in physics and beyond. There's really very few restrictions on these Fs. Great question. Okay, so I hope I've set it up. Now we'll get to the technical meat of like what we actually had to do. So one really cool thing about SDEs, okay, so the first technical problem is how to store the noise that we use on the sample on the forward solve to reuse it on the backward solve. So, like the forward solve of an SDE is actually just like a Monte Carlo, like a sample where we, let's say, conceptually sample an entire Brownian motion draw, and then compute an integral forward using that equation that I showed on the previous slide. Multiplying the Brownian motion by the diffusion function, then adding the drift function. So one thing that we usually need to do when we're doing constructing gradient estimators for stochastic variables or random variables is to somehow isolate the noise and use the reparameterization trick to have these parameterless noise variables. And this only became really popular in machine learning in like 2013, although it was sort of discussed in like 1992. But stochastic differential equations actually already do this. They already take all their randomness and stick it into this parameterless Brownian motion that never needs to have a parameter. So that was like one technical thing that had already been done for us 60 years ago, was all the noise is isolated into this Brownian motion. So we just have to somehow be able to like sample an entire Brownian motion and evaluate it wherever we want to, without taking infinite memory.
Sorry, it's not clear to me. What's the noise? What are you sampling? So describe in terms of the neural net or whatever, the computing.
So there's no, again, let's not worry about neural networks. This is just for arbitrary stochastic differential equations. If I want to evaluate one sample path from an STE, like for instance, I'm modeling a physical system and I want to say, okay, what if I start it in this state and then I run it forward? Obviously, I'm going to have to instantiate noise as I go. So that just requires us to sample a draw from a Brownian motion, like an entire function from a Brownian motion. So most SDE solvers, they just sample like Gaussians one step at a time. Like the Euler-Majorana, this sort of the simplest solver just says, okay, take a step in the direction of the drift, and then add a little bit of Gaussian noise that I just drew at that point. So they just kind of like sample noise as they go, and they end up with sampling a random walk. So we're basically asking, well, how do we sample random walks in a way that we can efficiently store all those samples, or somehow reconstruct them without taking too much memory, and also how to like zoom in between the samples that we evaluated on the forward pass, because the solvers on the reverse pass might need to like zoom in some parts to like take a closer look at what happened in that part of the time. Sorry, I'm not sure if that answers your question.
Yeah, we can go on.
Yeah. So again, we don't have to worry about neural networks here. Everything I'm talking about is just plain generic SDEs, and I'm only worried about scalability because I want to stick some neural networks into my drift and diffusion functions later. Okay, so there was this work from this guy, Terry Lyons, that talked about Brownian trees and basically said that, oh yeah, sometimes it's advantageous, instead of sampling Brownian motion by just sort of starting from the left and going forward, you can actually sample the middle of the middle of a Brownian bridge. Or yeah, so first sample the endpoints, and now we need to sample a Brownian bridge. We actually have a closed form for the distribution of like the marginal of any point. So we could, for instance, sample in the middle, condition on that, and then if let's say I'm trying to sample this point here, I could just do some sort of like binary search or like bisection where I just keep conditioning on the previous samples, finding the marginal distribution for the next point I want to sample, and sampling those, zooming in finer and finer until I get close enough to the point that I'm trying to evaluate. And the nice thing about this is that I can like throw away parts of the subtree if I want to, if I don't think I need them anymore. So that's fine. And the main technical, one of the technical contributions we made was to say, oh, actually, if you use random seeds that are deterministically generated, that are just a function of which branch they're on in this tree, you can actually always throw away all your samples that you made so far. And if I wanted to sample another point over here, I could just start with the same random seed and then deterministically update the seed based on which branch I'm on and sample any other points. So basically what we give is an algorithm that if you give it a random seed, it's already now implicitly defined an entire draw, like this infinite dimensional vector, this entire function draw that I can evaluate wherever I want to, up to like epsilon time error, in just log of epsilon, or log of 1 over epsilon time. So it's kind of cool. Like it came up sometimes, actually, I remember when we were in Cambridge, that sometimes we wanted to say, oh, I want to sample an entire draw from a GP so that I can like optimize it or whatever. But it's expensive because I have to keep around all the previous points. And this is a nice way, at least for Brownian motion, to like sample an entire infinite dimensional function at once, and then just be able to query it to whatever accuracy you want pretty quickly. Okay, and you know that might sound magic. The only thing is we just need this like little seed.spawn operation, which all it does is just like hash the current seed with like, you know, let's say like -1, 0, and 1 or something. Like you just have to do little hashing operations to make sure that the key is uniquely updated in a reproducible way. And then it just looks like a recursive like algorithm that just you know, goes to the left or the right and then calls itself again with like half the scale. Okay, so anyway, this is, I think, could be more generally used for anyone who's like writing algorithms for like sampling random processes. Okay, any questions about the random or the virtual Brownian tree? Okay.
It's like a connection, not so much a question, but it's like the general. I'd say this is like this is closely related to how we think about stochastic processes formally in like the theoretical foundations of probabilistic programming.
Okay, well, I'd like to take a look if you have any papers you'd like to point me to.
Yeah, I mean, so for Brownian motions in particular, so this type of representation gives you a point-wise representation. It's formally still kind of difficult to, it's generally need like an L1 type of representation. L1 representation is like in some sense like in an L1 type topology to integrate, and you can get ones like that by like combining this sort of idea with it looks very similar to this idea, so I'll send that to you. I'm not sure if it's useful, but yeah, there's some work on representing Brownian motions exactly under certain topologies.
Oh, awesome. Okay, yes, please do send that. All right. Okay, so the next one is a really funny mathematical detail, which is like, what does it mean to run an SDE backwards, right? I think no one has a problem with the idea for ODE, like you run this system forwards and then you can say, oh, I could run it backwards in time, right? Like this is sort of what Laplace was talking about when he said like, you know, the deterministic universe is perfectly predictable forwards and backwards in time. But somehow in the literature, it's like not really clearly, this question isn't really clearly addressed. And there's like reverse SDEs, but they're not, and backwards SDEs, but they're not the same thing as like just flipping time and saying, oh, maybe I could integrate this this stochastic this thing backwards in time. So, you know, I kind of like played around with this, and if you just by like make some simple arguments about the construction of like a Shertanovich SDE, that it seems like there's no reason why we shouldn't be able to integrate the same noise forward or backwards in time and get the same answer, right? So it's just, I'm saying, let's just slap some more negative signs on everything. Like for the deterministic part, you know, we're pretty sure it has to look like negative f negative t. And then for this part, it's like, yeah, we'll just also stick some more negative signs in there. It's easy to make an informal argument about this, but there was like a bunch of people saying it was somehow unknown or impossible. And actually I went to Leonard Wong, who's one of our co-authors on this work. He's a probabilist at U of T, you know, very serious measure theory guy. And he kind of laughed. He was like, well, what do you mean? Like you have a forward filtration that you sort of already run to get this sample. And now you're going to also like filter backwards again. It's like just like divide by 0. Like it doesn't make sense. And I also kind of, I don't want to talk about this too much because I don't know that much about rough path theory, but I was kind of saying, I think it's weird that I think SCEs kind of conflate the random variable part of things and the sort of non-differentiable paths part of things. And we could probably like separate these two things. And then Terry Lyons actually has been arguing for this for a few years, that we should really refactor stochastic theory into like these two different parts. And I totally agree. Anyway, So yeah, he kind of laughed at first, but then I sort of cajoled him into entertaining the idea that it could actually be as simple as this, and there had to exist a solution. And but like I didn't really contribute much to this part of the project, but basically they were able to prove that it is correct that you can construct a stochastic flow forwards and another stochastic flow backwards, such that when you compose them, you end up getting back to the same point. And that's sort of fine. And there's just a lot of, let's say, like mathematical crossing I's and dotting T's. And also, you know, Kunita, who's like one of the like original SCE guys, actually was sort of talking about this informally in some of his recent works, and that helped us out. Okay.
Sorry, quick question. So they said it exists, the reverse exists, but is it this reverse, or is it just that it exists?
So yeah, we showed that it exists and that it is these two stochastic maps, and that yeah, you just stick negative signs in front of these things in the Shatanovich form. I mean, if you use Ito, you have to add these correction terms. So yeah, we showed both. If that's answers your question.
You might like looking at non-standard analytic formulations of SDE theory, because I think it would be pretty straightforward.
I also thought about that too, and I was like, damn it, I wish I knew non-standard analytics, because I bet it would also be pretty straightforward. Yeah. So anyway, okay, so putting it all together, we had our old ODE adjoint sensitivity method. The SDE version is like the exact same setup, except that we have to have this extra diffusion function sigma, and we have to have an entire sample from a Wiener process, which, you know, it was kind of hard to maybe, but we could talk about that before, but it was hard to like implement it. And now we can just implement that with that algorithm we had before. And I mentioned before, we make these augmented dynamics for the drift, just the same way for the ODE. And then we just do the exact same thing for the diffusion. And we also sort of negate the noise. And so it's kind of like, again, just like negative signs in front of everything, just copy and paste. And now we can get the gradient of a scalar loss with respect to a single sample path drawn from an SDE solution by starting a system at the end of like the final time and running an STE integrator backwards in time to get all the gradients we want. So in expectation, these gradients will give us the gradient of the expectation of this loss with respect to these parameters. Yeah, so these are all unbiased simple Monte Carlo estimators for the gradients we want. So it's like a lot of math, a lot of algorithms to give us the simple, it's sort of like what you would guess the answer would be. Okay, any questions about,
like, yeah. Do you have to couple the noise backwards? Like, what if you just don't do that? Don't do that part.
Yeah, I thought about that. I mean, I'm pretty sure I'm pretty sure I wrote down a few examples where it's just like easy to show it would give you the wrong gradient. Like you don't even need the infinitesimal setting to do this, right? If you just have a standard Gaussian, and I imagine like doing the reparameterization trick for just a standard parametric function with one layer or two layers. I think it works for one layer, but it doesn't work for two layers actually. Then the gradients are just wrong.
And like technically, so when people talk about backward SDE, I think there's an initial condition rather than a final condition, right? And then they're trying to solve the system, or they have a final condition and then trying to work out with the initial condition. What is it? What's the difference? What's a backwards SDE?
Yeah, I'm not sure if I could give a sensible definition, but that's what I would say is that it's like you have another constraint about, like you maybe have one system that you define as forward dynamics, another one that you define as reverse dynamics, and an initial condition, and you have to figure out like some control signal that would get the system to a certain state at a certain time. But to be honest, that's not really my bread and butter, and I probably would give the wrong definition if I tried to. Okay, so this is something that like some people think this is trivial, that the time and memory cost of differentiation is like really important. And some people are like, no, just use forward mode. It's fine. Like how bad can it be? Like how many parameters does your model have? 100? Like whatever. And so I just want to say, if you have more than 1 million parameters, this is the only, you have to do reverse mode. There's just no way around it. And we could, of course, always backpropagate through the operations of our solver, And I would say we'll lose some guarantees about the gradients, and we'll just have a high memory cost. But if you have a small model, you should, or a small to medium-sized model, you should totally just backprop through the solver, right? Like that's probably going to be fine. Just have a small error tolerance in your solver. Okay, and we pay this log L cost for reconstructing the noise, but we don't think that's like a serious problem. Log L is upper bounded by 30 in real life. Okay, so the punchline is that now we can fit large SDE models by gradient descent in a way that I think we couldn't before. And I think this is like a real new algorithm, and it's people in like finance or whatever will want to use this. There is actually one last caveat, which is that if you just fit a stochastic model to optimize any scalar loss, then if you try to like learn the amount of diffusion, the optimal amount of diffusion will always be 0. Right? It's kind of like how the optimal policy in any non-adversarial game is going to be deterministic, provided you have like memory or whatever. So we can't just, or it's kind of like, if you add noise to any estimator at the last step and you try to tune the amount of noise, the optimal amount of noise is always going to be 0 for any deterministic loss. So will we actually, and also we want to have complicated likelihoods in our model. So, I was talking before about like patience, like latent state being something we might want to model. The likelihoods, the observations could be like doctor's notes or chest x-rays or some crazy thing that, doesn't look like Gaussian noise. There's a lot you can do when you have a Gaussian system with Gaussian noise. We want to be totally general and solve this sort of once and for all. So we're going to say we want to be able to handle any likelihood that's differentiable with respect to the latent state. So this could be like a text model or a convnet or anything. So we're going to again set up this sort of variational autoencoder framework where we have the generative model is, I have an initial state for my system. This is like my initial patient state. I have an infinite dimensional W. This is my noise of my state. So this is like all the slings and arrows, all the little interactions that happen in my system over the many years. And now we can, that's not normally drawn as like a single random variable, but because we have this nice construction, it's kind of makes more sense to do it that way. And then once we've isolated all the randomness into these two guys, and then once we know that and the parameters of our system, we can just deterministically solve our system forward with like one call to an SDE solver. To do recognition, it's like gets a little bit crazy. It's like if we're trying to fit more than one time series, we have to have a system that looks at all the data, outputs the parameters of an SDE, and then that SDE will implicitly define a approximate posterior over the trajectories of Z. So this is part maybe where I want to slow down a little bit, and I think this might be like something that Dan, I think especially, is going to really love, which is that, okay, I'm gonna get into this a little bit. So yeah, so the model is that we define F and sigma that say what is our distribution over F implicit or Z implicitly, in our likelihood noise model. And for inference, this is kind of crazy. What's our Q of Z, right? What's our approximate posterior over Z? We will define it with another SDE. And this is kind of great in the sort of probabilistic programming setting, which is that like this isn't the distribution over Z here is not a Gaussian. I don't actually know how to characterize the set of all distributions that can be expressed by an SDE very well. Like that's not something I know much about yet. But we're pretty sure that we're actually trying to work on proving this right now, that under some regularity conditions, this approximate posterior is like universal in that the true posterior will always be contained as long as we have a complicated enough drift function in our approximate posterior dynamics. So this is really cool. Like this is actually one of my favorite things, and this is one of the things we're doing with the follow-up work with, is to say, okay, well, we have this really powerful prior or like model over distributions. We can use that for variational inference with arbitrarily flexible approximate posteriors over infinite dimensional objects. And it's great because it scales really well. Like if this is a neural network, if I want my approximate posterior to be more complicated, I just make my neural network a little bit bigger. So yeah, so I'll let Dan stick that in his pipe and smoke it later. But yeah, to me, I think this is also something kind of new under the sun. And actually, going back to like this CVL like in Cambridge, I remember walking around the halls being like, oh, I want to like fit an infinite dimensional, infinite layer neural network someday or whatever. And now we actually can. Okay. So also, if you've been following neural processes, which I actually don't really like that line of work very much, you can kind of view this as sort of like neural processes done properly.
Okay. Quick question, David.
Yeah.
So the B at the top here is the Brownian motion, and you've drawn it as like a single Brownian motion. But if I'm not mistaken, like you could these times T1 I guess are random, right?
They're not necessarily random. I mean, yeah, I guess I didn't really talk about that. It's kind of hard to draw in a graphical model notation.
Yeah. Okay. Well,
it could be random, yeah.
If they were, even if they, let's say that, let's ignore that. But I could carve up time, and now I would actually have a Brownian motion for each chunk of time, and they would be independent a priori.
Well, they wouldn't be independent because the end of one path has to meet the beginning of the next path.
Right, but I mean, if I'm not mistaken, like the STE is driven by the changes, right? I mean, the integral is sort of not really relevant to the STE, right? I mean, isn't it just the instantaneous? Isn't it the white noise process?
Yeah, yeah. Maybe there's some non-standard analysis way where we can replace all our Brownian motions with white noise. I'm not really sure.
Yeah, but like I don't know. Like I kind of feel like say I actually gave you like two Brownian motions that weren't lined up. Like how would your code change? Like all it would do is like when you cross that boundary, you would just temporarily put the two Brownian motions to line up, right?
But you'd have to, otherwise you would get this like giant delta.
Yeah. No, you would put them up, but what I'm saying is that is not a priori dependence. That is dependence that's induced, like in some sense. Or I'm not even sure if that really really the only dependence that induces is like if you somehow like if your little chunks of time cross a boundary and now you've linked them. But like if you were to conspire to cut time in your simulation of your STE right exactly at the boundary, it wouldn't really matter if you
yeah, I think that's a fair point. Yeah.
So I mean, when I see this model with this B here connected to everything, the back of my head I get a little nervous because that's hard to integrate over that. But I think the dependency structure here is sort of simpler than that.
Yeah, I think there's a sense in which you're right. I will say that the way we're going to integrate over all this is simple Monte Carlo and variational inference. Anyway, I want to get to the end of this before we get too deep into any of these nice ideas. Okay, so the last bit of math. This is the end of the technical contributions, and this is sort of already known. What's the Kirsanov's theorem? Is the sort of more general version of this that basically says, okay, I can actually get an unbiased estimate of the KL divergence between, or the KL divergence between the distribution on functions defined by two SDEs by just running an SDE forward with these funny dynamics. So it is that we have a prior that we've defined somewhere, and maybe this is just like an OU prior or some simple thing, who knows what. Then we have our approximate posterior, which actually has to share the diffusion with the prior, otherwise the KL divergence is infinite. That seems like a major restriction, but it's actually not, and I'll show that on the next slide. So we're learning this approximate posterior dynamics. Then our elbow, this LVI, I should have just written elbow. This is the standard elbow, but with like infinite dimensional variables. It's got our log likelihood, standard thing. And then this is the like log P minus log Q thing, or the KL thing. And that just looks like integrate through time the difference in the drifts divided by the diffusion. And that kind of looks like the KL between two Gaussians, even if they share the same standard deviation. So basically, the more work that the posterior is doing to like steer the path into a particular part of space, the more the KL divergence is. So we can just stick this on as another part of our state into our SDE solve, and now we have this like infinite dimensional stochastic variable inference method. So this is like, it's like everything just worked out perfectly. And there's actually a whole bunch of details about non-diagonal noise and Milstein solvers where like everything cancels out just barely so that we can still use efficient solvers. Like it feels like God is on our side in this one. Okay, so end of math. Even if your friend said we only can handle an hour of math in a row. Here's us fitting our approximate posterior to our prior. So again, so a lot of SDEs define Gaussian processes. So just, I don't know, for familiarity's sake, we'll use an Ullstein-Uhlenbeck prior. The nice thing is that our posteriors here are like any crazy crap that the posterior SDE can define. So we can use non-Gaussian likelihoods, and nothing needs to change in our code. So just for the sake of example, we use a Laplace likelihood, right? You can use anything. And now this is watching training. This is watching us fit the parameters of our Q, like our phi, like the diffusion for the posterior, to the elbow that has a little Laplace likelihood around each of these little crosses. And it does the right thing, right? Like this looks kind of like maybe it is the posterior of a GP under a Laplace likelihood, right? And it does the right thing where it's certain where the data is and it's uncertain where the data isn't. Maybe a few of these examples. And here I've actually shown in gray, this is the drift of the approximate posterior. And so basically, the prior would have sample paths just kind of going out in a cone, but the posterior steers them towards the data. And that's why these purple sample paths, go through the data for the most part.
Is there, I'm kind of curious, right? Like there's nothing really in the data, and it seems like a very rare situation that you would ever have had simulated the case where you got to the top of this plot, right? And you actually had to like rely upon that vector pointing you back.
Oh,
down.
You're saying what's training the network over here?
Yeah, that's what I'm exactly after.
Yeah, that's a great point. I think you're right that if our sample paths during training never went up there, that there wouldn't be a gradient for this part. And that it's just that the neural network is kind of smoothing things out. I never thought of that. That's a great point.
I'm curious what kind of neural networks have led to good performance, and is it any different from like what works well in vision?
I mean, we just use sort of standard MLPs for all this stuff because there's like, at least for these toy examples. Yeah, I bet there's like a whole new art of how do you define or design these neural network architectures, but we don't have much insight into that yet. It would be cool to show these. Yeah, so you can see these things wiggling around during training. So yeah, this is, yeah, so Zoychen Lee did the experiments. This do seem like suspiciously nice initialization, actually. Yeah, you can see them wiggling around. Yeah, probably these should be like even more strongly forcing down. Who knows? Okay, so now we have a new model class, right? Like, imagine if you invented GPs, right? Like, okay, obviously we're not saying invented SDEs. I'm saying now we have computational tools to fit these large latent SDE models. And this is like new. Oh yeah, I'm not going to have my own stuff that correctly, but yeah, we can fit this data. Here's us, and again, this works with any likelihood, and the same code. It's automatic differentiation, variational inference. Works in it works in principle. Everything's slow. We've only scaled this to like 11,000 parameters, but I'm kind of annoyed because I think I think there's no reason why this shouldn't scale to 1 million, and we just haven't run those experiments yet. But here's us having fit our SDE model to mocap data, for instance, which is 50-dimensional data, 6-dimensional latent space, lots of different time series that we're sharing the dynamics parameters across, and it has the best predictive MSE, which I think makes sense because it's again generalizing the previous models.
Can you unpack this a little bit? What's going on here? What your data are? What exactly you're visualizing?
Sure. So the data are time series, but instead of having one observation per time, we have like 50. And then we have, I think, however long these are, there's like 200 frames in each time series, right? And I think we have like a few hundred of these time series. So now we can say, okay, well, we think the dynamics of like human walking is the same, but maybe like there's like some initial state or some global state that's different per person. We're also learning this recognition network that takes in a series of like the whole data set and then outputs the parameters of the approximate posterior for that particular person. Right, but that's all just like inference. Once we have the elbow, we don't have to use recognition networks. We could just, we can use I guess we can use Monte Carlo, but we could use just stochastic variational inference, gradient based variational inference, whatever we want. The point is we have gradients.
So is this a visualization of the forward dynamics?
This is a reconstruction of a path, I think. I forget if it could be that or a sample from the final dynamics. And it's kind of floaty. Like, I don't think it's actually completely nailing the dynamics, to be honest. I'll just say it's doing better than the previous continuous time models in this set. So this is very early days. Most of the work in this paper was like the mathematical and algorithmic stuff. So yeah, okay, so just to reiterate, we generalized the adjoint sensitivity method to SDEs. Now we have like the same time cost. It's all automatic. It can all be like tidied up very nicely. And I guess I didn't really mention the details about the elbow, but you can do infinite dimensional variational inference, which is fun. So now here's where I kind of want to get feedback from you guys, because I think there's a lot of directions we can go here. There might even be some foundational issues that I haven't addressed. So one is like, okay, we obviously want to make these like stationary. Also, I think it's easy to make multi-timescale models where there's like the slow dynamics that affect the faster dynamics, and we can even like maybe skip modeling the like fine details in some settings. Also, I bet that we could write the exact same paper almost, but with jump processes, right? Like and maybe like work out how to have the Brownian tree construction, but for like Poisson processes or something like that. There's also the possibility to try to convert this method to solving high-dimensional PDEs. I haven't really thought about this. This is like something Chen is kind of excited about. Also, for the virtual Brownian tree, we were only doing samples, but we actually, if we could also sample the integrals of those, like if we want to use higher order stochastic Runge-Kutta solvers, like right now we're only using order 1 solvers, which is like pretty high by SDE solver standards, but pretty low by ODE solver standards. We need to like augment the virtual Brownian tree to also sample integrals of the Brownian motion. And then, yeah, now we still haven't got the code out, but I really want to do some applications to like population genetics or finance or even maybe epidemiology. I mean, epidemiology is probably a bad example because like I think all the data comes daily anyway, so like you probably could just make a discrete time model and it's fine. But there's all these people fitting SDEs, but they never fit them to more than like 10 or 20 parameters for the most part. Or they do something terrible like approximate Bayesian computation because they can't differentiate through their samples. So I think this could have a lot of applications. And then the thing I'm working on for NIPS is exploring this like arbitrary flexible posterior and doing infinitely deep Bayesian neural networks, which is maybe a little self-indulgent, but it's very fun. And it's a good chance to like round out some of the theoretical issues. So we had the code working. This was all done in like December or January, I forget. And then the student every week has been like, I'm going to get the code polished out and out next week. And I think he's just gotten distracted. And it's like, so I've actually just started doing an end run around him and coding this up in JAX, which is like an amazing numerics framework. And we actually have most of it written in. So hopefully in a few weeks we'll have it out. Okay, so I'm going to skip over the regular work unless you guys are interested. The main point is everyone else is just using Euler discretizations, and we're solving everything exactly and letting adaptive SDE solvers do the heavy lifting. and I want to say that like this guy, Zhuai Li, really is amazing. Leonard Wang actually did the hard measure theory parts of this, and Ricky and Yulia helps do the coding. So anyway, thank you very much.
All right, thanks for the great talk. Any questions for David?